Good evening, ma'am. I am Manish Sharma from CSE B section. Today, my topic for CIE 2 is knapsack problem. We move for introduction to knapsack problem. The knapsack problem is a classic optimization problem in computer science. It involves selecting items with given weights and values to minimize total value without exceeding a weight limit. The problem has numerous applications in resource allocation and budget management. We move for problem definition. Give a set of items, each with a specific weight and value. The goal is to minimize value while adhering to a weight constant. The knapsack represents the capacity limit that cannot be exceeded. The problem can be classified into different types, such as 0 by 1 knapsack and fractional knapsack. We move for definition for specific gravity. Specific gravity or relative gravity is a dimensionless quantity that is defined as the ratio of density of substance to the density of water as the as at a specified temperature and pressure. The gravity formula is specific gravity formula is density of object by density of water by object and pHO. Types of knapsack problems. The 0 by 1 knapsack problems allows each item to either included or excluded, but not partially taken. The fractional knapsack problem allows items to be broken into smaller pieces, enabling partial inclusion. There are also variations like the multiple knapsack problem, which involves multiple knapsacks with their over capacity. Mathematical formulation. The problem can be mathematically expressed using variables for weights and values. The objective function aims to maximize the total value subject to the capacity constant. Formalization can be represented as maximize summation value of I. Mathematical formulation. A common choice to find the model parameters is by minimizing the regulated training error given by L is a loss function that measure model fit. R is a regulation term. The penalizes model complexity. Move for dynamic programming approach. The dynamic programming approach breaks the problem down into smaller subprograms for efficiency. It uses a table to store results of subproblems, avoiding redundant calculation. This method is particularly effective for a 0 by 1 knapsack problem. We move for greedy approach for fractional knapsack. The greedy approach is optimal for fractional knapsack problem as it prioritizes the highest value to weight ratio. It are sorted by their value to weight ratio and the algorithm iteratively fills the knapsack. This method does not guarantee an optimal solution for the 0.1 knapsack problem. We move for complexity analysis. The time complexity of the dynamic programming solution for 0 by 1 knapsack problem is big O of NW, where N is the number of items and W is the capacity. The greedy approach for the fractional knapsack has a time complexity of big O n log n due to sorting. The problem is NP complete, indicating that no polynomial time solution is known for the 0 by 1 variant. We move for particle application. The knapsack problem is widely used in resource allocation scenarios, such as cargo loading and budget management. It can also be applied in finance for portfolio selection and logistics for shipment planning. Additionally, it appears in various fields such as cryptography, network design, and machine learning. And the related problems. The knapsack problem is closely related to other combinational optimization problems such as the subproblem. It also has connections with the traveling salesman problem and the big packing problem. Understanding the knapsack problem can provide insights into solving these related challenges. Conclusion. The knapsack problem is a fundamental problem with significant applications in both theory and practical application. It illustrates the challenges of optimization and resource allocation in constrained environments. Further research continues to explore efficient algorithms and heuristics for solving various forms of the problem. Thank you, ma'am, for listening my presentation.